Now, the next example is morphine, C17H19NO3, and this is an alkaloid that's a pain reliever, and we have a 0.0075 molar solution of morphine and at 25 degrees Celsius, and we're trying to find the pH of this solution. Well, if we know the K sub B value, and again this is a number that can be found in tables, then we have pretty much the same problem as we just did, but now for a base rather than an acid. And of course we have to remember that what bases do is dissociate water, and so this base, morphine, will make its conjugate acid, which is the same formula but with an H plus added on, and then OH minus comes from the dissociation of water by this base, and our initial concentration is 0.0075, where again we pretend it hasn't done any dissociating of water, and then we let it do the dissociation of water, so our standard plus X and minus X gives us equilibrium concentrations as indicated in terms of X. And then, as always, we do our equilibrium constant expression. This time it's K sub B. And when we do this, what we know is, since we've found the value of K sub B for morphine, then we can plug that into the equation. We know in terms of X or we have an equation, I should say, in terms of X. So we can solve for X, and we get, in this case, 1.1 times 10 to the minus 4th molar. Now, again, in previous problems, this might have gotten us essentially to the end of the problem. We find the equilibrium concentration of some substance, and then either we're done or we use that to find the equilibrium concentrations of other substances. But as with the previous problem, we're interested in finding pH of the solution. So, to find pH of the solution, we note that what we solve for, X, is actually the concentration of OH minus. And now, if we know that the concentration of OH minus is 1.1 times 10 to the minus 4th, there's a couple different ways you can then find pH. One possible way is to note that pOH is the negative log of the concentration of OH minus, and that is 3.96. And then since pH plus pOH adds up to 14, then pH is 14 minus pOH, which is 14 minus 3.97, which is a pH of 10.04. And that seems reasonable to have a pH above 7 for a basic solution. And it's worth noting, and we'll use this in the next problem, that the K sub A for a weak acid and the K sub B for the conjugate base of that weak acid can be related by the equation shown here, which is that the product of the two, K sub A for the weak acid times K sub B for its conjugate base, is equal to 1.0 times 10 to the minus 14th. The same value as for Kw for the autoionization of water. And it's really important to note that K sub A is for an acid, a weak acid, and K sub B is for the conjugate base of that acid specifically. So if we have a question such as this, we have sodium hypochlorite, NaOCl. This is the active ingredient in bleach, so if you look on a bottle of bleach, you'll find that listed as the main ingredient, and we'd like to find the pH of a 0.250 molar solution of sodium hypochlorite, NaOCl. Now, when we look for a value for sodium hypochlorite's K, we typically won't find that. But what we will find is a K sub A value for hypochlorous acid, HOCl. And we note that HOCl is, of course, an acid. Its conjugate base is OCl minus. And OCl minus is part of NaOCl. The Na plus is a spectator ion, so the OCl minus is a base, and that's going to be what we use for our calculation. So K sub A times K sub B in general is 1.0 times 10 to the minus 14th. That means K sub B is 1.0 times 10 to the minus 14th over K sub A for the conjugate acid. If we have OCl minus, we'd like to find the K sub B for. Then we use the K sub A for HOCl, and that is 1.0 times 10 to the minus 14th over the K sub A for HOCl is 3.5 times 10 to the minus 8th, and that gives us 2.9 times 10 to the minus 7th. And now this is what we're going to use in the rest of the problem to find the pH of sodium hypochlorite. So we note that NaOCl is going to dissociate water, but really it's the OCl minus part of it that's going to do that. So we drop the spectator ion Na+, and we write OCl minus plus H2O. Note that what's going to happen is OCl minus, the base, will grab an H off of the H2O to make the conjugate acid HOCl. This is the conjugate acid of OCl minus. And then we get OH minus left when the water is dissociated by the base. And now we're back to our standard ice table stuff. We have a 0.25 molar solution. We pretend it hasn't dissociated yet. We let it do its dissociation. So plus X and minus X types of things. And at equilibrium, we have the concentrations as shown. We do our equilibrium constant, and again, it's for the base. So it's a K sub B for OCl minus. We just found out that the K sub B value for OCl minus is 2.9 times 10 to the minus 7th. So that's equal to X squared over 0.25 minus X. And when we solve, in this case, we get X is equal to 2.7 times 10 to the minus 4th molar. Now, of course, that is the OH minus concentration, and we're interested in pH. So same thing as we have done in the past. The OH minus concentration is 2.7 times 10 to the minus 4th. We take the negative log of that, and we get 3.57, and that's the pOH. And then the pH is 14 minus 3.57, which is 10.43, and that is our answer.